What's up, everybody? Welcome to a chemistry notes video on ways to analyze the Lewis structures we had been talking about drawing over the earlier points in this unit. So one of the things we can look at for any Lewis structure is the polarity of the molecule. All right, polarity of the molecule is just how is the charge of the electrons in the molecule, how are they distributed throughout the molecule. Molecular polarity, again, just the distribution of charge throughout the molecule. And kind of like the polarity of a bond, we use the same exact two words to describe the polarity of a molecule: nonpolar and polar. Well, nonpolar molecules have an equal distribution of charge throughout the molecule. All right, and we're going to just do some general trends here. We're not going to go deep into the math behind the charges or anything, but just generally speaking, you need two things to be true. All right, for the a molecule to be nonpolar. All right, and the first of these is all of the atoms bonded to the center atom need to be the same. All right? Now, they are different from the center atom. We're not dealing with a case like ozone here, where those center atoms are different. All right? Where the center atom and the surrounding atoms are the same. We're dealing with a case here where all of the bonded atoms at the center are the same. So whatever around the center atom is identical to each other. And we're also trying to take a look at that center atom, and we're looking for no lone pairs of electrons on the center atom. And remember, in the Lewis structures, lone pairs are represented as dots. So that center atom is not having any dots. Now, if we get into the world of organic chemistry, it gets a little bit more complicated because we treat carbon bonded to hydrogen the same way as we treat carbon bonded to carbon, but we're not really dealing with organic molecules here and organic structures. We're looking at just general basic Lewis structure shapes. The second type of polarity is when there is an unequal distribution of charge. All right, and this is called a polar molecule. It's called a polar molecule because there are two poles, two opposite ends. There's a positive end and a charge and a negative end. All right, and there needs to be, again, a couple of things. First, there has to be some type of polar covalent bond. All right, so we're looking for two different nonmetals bonded together that are not carbon and hydrogen. This will kind of take out of play all of those big organic compounds that have a lot of carbon-hydrogen bonds. All right, just kind of takes away all the hydrocarbons, unless like there's also oxygens or nitrogens in there. So it just takes those out of the equation. So we're looking for two different nonmetals or two different nonmetal and metalloid atoms bonded together. All right? And then we are looking for asymmetry, so something that's not symmetrical. The easier way of seeing that, especially if you're just using a two-dimensional drawing, is that the center atom has lone pairs or dots in the Lewis structure, or the atoms bonded to the center atom are different than each other. All right, so if you have a carbon atom bonded to three hydrogens and a chlorine, all right, this is an example of the atoms bonded to the center atom is different. All right, and that would make it polar. And if you just look at the picture, one of the things you can see is look at all the electrons here around the chlorine. Those hydrogens don't have all those electrons. So there's more negative charges at the chlorine, less negative charges over on the other side. So the side with the chlorine is more negative, which means the side without the chlorine is more positive. That's what we call polarity. So let's look at some examples here. Our first example, we have CH4, good old methane. Methane is nonpolar. Why? Well, all atoms bonded to carbon are hydrogen, and there are no dots on carbon. All right, so it doesn't have different atoms bonded to carbon, and it doesn't have dots. All right, compare this to number 2, where we have a carbon, and, well, this is a wrong thing. We have a carbon, a hydrogen, and 3 chlorines. This one is polar. And it's polar because 2 different atoms are bonded to the center atom, in this case, the carbon. Number 3 is also polar, and this time you're saying, well, it's both bonded atoms are hydrogen, and that's true, but there's also these lone pairs, and lone pairs are different than a pair bonded to hydrogen, so there's no symmetry in 3 dimensions. It's really hard to see a symmetrical 3-dimensional situation with a 2-dimensional drawing. So that's why I say look for the dots. All right, and so there are lone pairs on the oxygen. All right, there are dots on the oxygen. Number 4, hydrogen fluoride, HF. Missing a couple dots for my F there. All right, again, no symmetry. All right, this is polar. A lot of electrons on the right-hand side, no electrons really on the hydrogen left-hand side. So there's a lot of negative charges with the F, not a lot on the H. Number 5 is another nonpolar molecule, CO2, carbon dioxide, right? And it's all atoms bonded to C are the same, and no dots, no lone pairs on the carbon. Number 6, ammonia, polar. There's a lone pair on the nitrogen. Number 7 is nonpolar. All right, there's no polar, and I'm spelling that wrong. There are no polar bonds here in number 7. Okay, only N nitrogen bonds. And nitrogen to nitrogen, they're going to share their electrons equally because they're the same element and have the same electronegativities. Finally, number 8, also nonpolar. Again, the surrounding atoms are the same, and no lone pair on boron. All right, that's how you tell polarity. You're looking, are there different atoms bonded to the center? Are there lone pairs? If you can answer yes to either of those questions, chances are you have a polar molecule. We'll find out how that changes the chemistry of the molecule and the physical properties of a sample of that molecule later in a different unit. Right now, we're just looking at these molecular pictures, these Lewis structures, and trying to decide, is the distribution of electrons equal or not equal? All right, nonpolar means the electrons are equally distributed. Polar means they are not equally distributed. The other thing we can do with Lewis structure is we can find something called the molecular geometry or molecular shape. All right, it's the easier way to look at it. All right, and there are a bunch of shapes. Here are 8 that you might see. Out of these 8 possible shapes in this picture here, there are more than these 8. Just these 6 are the ones you really need to know. And if you look, these first 2 are both linear. It's just one has 2 atoms, one has 3. All right, so there are 5 basic shapes that you need to be able to identify. Those 5 are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. All right, the other ones like trigonal bipyramidal or octahedral or seesaw and T-shaped, these other ones that I'll bring up are more advanced shapes, and they all happen when the center atom expands its valence electron count to 10 or 12 electrons instead of the standard 8. We're going to just focus on the 5 shapes that can occur when the center atom has 8 valence electrons. So here are those 5 basic shapes. These are the only ones that I would ever ask you to draw, and these are the only ones that I am going to ask you to identify in this class. There are more that exist. They are possible. But those other ones all happen because the center atom goes beyond 8 valence electrons. All right, we're not really getting into those too much. And the big key to cause the difference between shapes, all right, are those lone pairs on the center atom. The lone pairs are 2 electrons. They're still electrons, so they affect other electrons, including electrons and bonds. So if we look at linear, any molecule with two atoms is linear. It's always going to be linear. There's no other shape they can make. It's having 2 points. It's always a line. All right? If you also have 3 atoms with no lone pairs on the center atom, we end up seeing it's making a line. Carbon dioxide is an example of this. However, if you have those 3 atoms with a lone pair, or more than one lone pair, like in the case of water here, these 2 pairs of electrons that are on just the oxygen repel the bonds and kind of push the line down, creating an angle, which is why sometimes these bent shapes are called angular. I tend to like the word bent better. It just looks like a bent line. Similarly, there are two shapes that start with the word trigonal, which makes you think of 3. All right? Both trigonal shapes have 3 bonds. All right? The big difference, the pyramidal has a lone pair, as in ammonia here, the second one. That lone pair pushes the bonds down and creates like a little tiny pyramid. Whereas in boron trifluoride here, there's no lone pair on the boron because boron is happy and satisfied with the 6 electrons and the 3 bonds. All right? So everything is in the same plane of existence. It's essentially a 2-dimensional type of shape. And so because everything's in the same plane, they call it planar. Because these 2 electrons push down the hydrogens, it creates what looks like a little pyramid. They call it pyramidal. Finally, if we have 5 total atoms, a center and 4 surrounding atoms, all right, we get a shape called a tetrahedral. Tetra, remember, means 4. So if you have a center atom and 4 bonds, it gets this tetrahedral shape. All right? And this shape only happens when there are no lone pairs on the center, because that center atom has 2, 4, 6, 8 electrons. As I said, the center atom can go beyond 8 in special cases, and that brings a whole new variety of shapes. You need to know that there is this possibility for like a true-false question, but you don't need to memorize the shapes. You only need to memorize and go through and internalize and know these 5 shapes. Really quick, all right, these advanced shapes, these are what I alluded to on the last page. All right, they are what happen when there's more than 8 electrons on the center atom. All right, we get shapes that are called trigonal bipyramidal or seesaw, T-shaped, square pyramidal, square planar, and octahedral. And you can see in these, in the trigonal bipyramidal, 2, 4, 6, 8, 10 electrons around the center atom. Well, that's more than 8, right? Happens in special cases. All right, second one down, 2, 4, 6, 8, and then a lone pair is 10. All right, T-shaped, 2, 4, 6 electrons and bonds, 8, 10 when you count the lone pairs. Again, it's going beyond those 8. All right, so the advanced shape happens because the center atom has more than 8 electrons. All right, you just need to know that these exist. You don't need to be able to identify them. You're not going to have to draw any of these. right? Just know the possibility for them exists. And finally, we're going to just do a couple more practice questions of drawing, all right, that we have not done yet. So here we go. There's these 7 steps for drawing anything. Neither of these examples, C, Br2, Cl2, and N, Br3, none of them are ions, so we can start out by knowing we're not going to deal with step 7. We're also not going to deal with adding electrons for negative charges or subtracting electrons for positive charges because these are compounds, there's no charge. All right, so we're going to place the underlined atom in the center. In this first one, the underlined atom is carbon. So carbon goes at the center. We're then going to single bond it to everything else. So there are 2 Brs and 2 Cls. After that, we're going to go in and we're going to add in lone pairs or dots so that everything has 8 electrons. The carbon already has 2, 4, 6, 8 electrons in the 4 bonds, so carbon gets no dots here. Bromine, however, has 2 electrons in the bond, so it gets 6 dots to get a total of 8. And that's going to happen for both bromines. 2 electrons on each of the other 3 sides. Chlorine is in the same boat. Each chlorine gets 6 dots around it because it needs to get to 8, and it only has 2 electrons in the bond that it has. Now I'm going to count up everything I've drawn. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, there are 32 drawn electrons. Now I shoot over to a periodic table to look up the valence electrons and everything. I have a carbon, which has 4, 2 bromines, which have 7 each, and 2 chlorines, which have 7 each. Add all these up. 7 plus 7 is 14, plus another 7 is 21, plus a 4th 7 is 28. 28 plus 4 is 32 valence electrons. (32 minus 32 is 0, which means the picture I drew is the answer. In my second example here, I have nitrogen tribromide. We get a nitrogen. There are 3 bromines around it. Nitrogen has 6 electrons in the 3 bonds, so it gets 2 more electrons as dots. A little bit of a glitch here. There's the 2 electrons. Each bromine has 2 electrons in a bond, so each of the bromines gets 6 dots to get it up to 8. Remember, hydrogen only wants 2. Boron, which is just a plain B, wants 6. Bromine is Br. That's why it gets 8. Now, we'll count everything up. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons in my drawing. I now take a nitrogen, which has 5 valence electrons, and 3 bromines, which each have 7. 5 plus 7 is 12, plus 7 more is 19, plus that final 7 is 26 valence electrons.